Hello friends, welcome to my YouTube channel Math Easymatics. Our today's topic is rank of a matrix. Let's get started. In this video we are going to learn elementary operations, row echelon form and rank of a matrix. First, elementary operations. There are three elementary operations. First is interchange of any two rows or columns. It can be represented as Ri interchange with Rg. For example, let's take a simple 2 by 2 matrix. Here we interchange R1, R2, interchange these two rows 3, 4, 1, 2. Next is multiplying all elements of a row or column by a non-zero scalar k. It can be represented as Ri replaced by KRI. Let's take the same example. 4 R1 replaced by 2 R1. So we get 2, 4, 3, 4. Next is addition of elements of ith row or column by equimultiples of jth row or column. It can be represented as Ri replaced by Ri plus K Rj. So we take R2 replaced by R2 plus 2 R1. So here we get, so these are three elementary operations. Next is elementary matrix. Applying single elementary row or column operation on identity matrix, we get elementary matrix. Let's take a 3 by 3 identity matrix. Perform any elementary operation. Let's take R1 interchange with R3. We get 0, 0, 1, 0, 1, 0, 1, 0, 0. This is an elementary matrix. Let's name it E1. Another operation, R2 replaced by 2R2. So multiply this second row by 2. First row and third row will be as it is. 0, 2, 0, 0, 0, 1. Let's name it E2. So E1 and E2 are elementary matrices we got from simple elementary operation on identity matrix. Next is equivalent matrices. Let A be any matrix. By applying number of elementary transformations on A, consider we get a matrix B. Then B is called matrix equivalent of A, denoted by A equivalent to B. Let's take a 3 by 3 matrix. 2, 3, 5, 4, 1, 7, 2, 1, 1. Consider is that, say it is matrix A. Now perform any elementary operation. Let's say R1 interchange with R3. So here we get 2, 1, 1, 4, 1, 7, 2, 3, 5. Another, let's take R2 replaced by 2R2. Here we get 2, 1, 1. Multiply this row by 2. 8, 2, 14. Here we get 2, 3, 5. Let's say it is B. So here we get B is equivalent to A, or A equivalent to B. from the above definition, as we have performed elementary operations on A and got B. Here, if we take an elementary matrix, let's take this operation and create an elementary matrix. As this is 3 by 3 matrix, so we will need 3 by 3 identity matrix. 0 0 1. We know that by performing single elementary operation on identity matrix, we get elementary matrix. So let's perform this operation. Here we get say this is E1. Now multiply E1 with A. So 2 3 5 4 1 7 2 1 1. Here we get multiply this and A, E1 dot A. So here we get 2 1 1 4 1 7 2 3 5. Here we get this matrix and this matrix similar. By performing elementary transformation on identity matrix, we got an elementary matrix, and after multiplication of elementary matrix on with A, we got another matrix which is similar to the elementary operation done on A. This and this. Another method to perform elementary operations. So next is row echelon form. A matrix A of m cross n is said to be in row echelon form if 0 rows, if any, occur, then they must be below the non-zero rows. Consider a 0 row. First point tells us that if any non-zero row, this is a non-zero row because all elements are not 0. So every 0 row must be below non-zero row. Second point is number of zeros before first non-zero element in each row is less than number of such zeros in next non-zero row. Let's take 1 2 3 4 and something, and here 1 2 3 and something. Here we see that number of zeros in this row is less than the number of zeros in this. Here number of zeros are 0 and here number of zeros are 1. That's the second point. Third point is 0 rows may have equal number of zeros. As we saw from the first point that 0 rows are always at the bottom in row echelon form, so it doesn't matter. Next is method to create row echelon form. First row and first column element is to be non-zero if possible. So this should be non-zero. Here any number of zeros or non-zeros can be there. We don't consider this part. Only first leading element is important in row echelon form. Using R1, make first column elements A21, A31, A41 as 0. This is A11. This is A11, first row and first column. This is A22, A33. This is A21, A12, A13. This is A23. This is A31 and this is A32. Using R1, make first column elements A21, A31, A41 as 0. So we have to make this 0. As we have studied in row echelon form, if here we have 0 zeros, then here there should at least be 1 0. We have learned this in the definition of row echelon form. Same goes for here. Using R2 make second column elements A3 to A4 to A5 to 0. So these elements should be made 0. Same definition applies here. As here it is 1 0, here there must be at least two zeros. Again goes A4 3 A4. Here, as here are two zeros, the row below it should have at least three zeros. That's what it means. Let's understand it with an example. Take a 3 by 3 matrix. One, two, three, 3, 4, 5, 4, 6, 8. Now we have to eliminate this, and then we have to eliminate this as per the method. So first take R2, replace it with R2 minus 3R1. R2 here, R2 first element is 3. If we multiplied 3 here, we will get 0. Same applies for the third row, R3, replace with R3 minus 4R1. So here we get 1 2 3. Here we get 0. Here we get minus 2 and minus 4 minus 4. Now we have to make this element as 0. So we take R3, replace with R3 minus R2. So here we get 1 2 3, 0 minus 2 minus 4, 0 0 0. So this matrix is in row echelon form. See, here we have 0 zeros, here we have 1 zeros, and here we have 3 zeros, as it is a 0 row. So next, first is submatrix. A matrix obtained by deleting some rows or columns or both of a given matrix. Let's take a matrix 1 2 3 4 5 6 7 8 9. In this matrix, if we want submatrix of order 1, submatrix of order 1 will be each element of this matrix. So 1, this will be submatrices of order 1. If we take 2 by 2 matrices, let's say 1 2 4 5, now 2 5 3 6, these are matrices of order 2, and submatrix of order 3 will be this matrix itself. So these are the square matrices. If we want, we can also take 1 2 3 4 5 6. This is also a submatrix of order 2 by 3. Next we have minors, determinant of a square submatrix of a matrix. So in order 1 the element itself will be the determinant. In order 2 we have to take determinant of this, so it will be 5 minus 8 minus 3, and here it will be 12 minus 15 minus 3. Same goes for the order 3 matrix. Next is the rank of a matrix. A non-negative integer R be rank of a matrix A if there exists at least one non-zero minor of order R, and all minors of order R plus 1, if they exist, are 0. That is, rank of A equals order of highest non-zero minor. This definition implies that order of the highest non-zero minor. We know that minor is the determinant of square submatrix of the matrix. Here it says highest non-zero minor. So In this example, the highest order is of 3. So let's check minor of order 3. If we take determinant of this, we get 0. As here it is said order of the highest non-zero minor. So 3 is not the rank of the matrix. Let's take any 2 by 2 matrix. In this 2 by 2 matrix, we get minor as -3, which is non-zero. So rank of matrix will be 2 for this matrix. Let's understand this both definition. First is there exists at least one non-zero minor of order R. We have got here rank equals 2, R equals 2. They have given there exists at least one non-zero minor of order R. So of order 2 we have got at least one non-zero minor. So first condition is satisfied. Second condition is all minors of order R plus 1, if they exist, are zeros. So R is 2, R plus 1 we get 3, and minor of order 3 we get 0. So this condition is also satisfied. So here rank of the matrix is 2, which is order of the highest non-zero minor. So next we'll see properties. If rank of A is 0, A is a null matrix. In null matrix we get all minors as 0. So rank of A equals 0 is only possible when A is a null matrix. Next is if A not equals to null matrix, here it is null matrix, then row of A is always greater than or equal to 1. If you take any matrix which is not null matrix, you will always get rank greater than 1, greater than or equal to 1. So here if we take this matrix and perform R2 minus R2 replaced by R2 minus R1, here we get 0 0. So this is of rank 1. So if a matrix is not a null matrix, then it will always have a rank greater than or equal to 1. Next point is determinant of A n cross n is not equal to 0, then row of A n cross n equals to n. For this let's see the previous slide. Here we have seen that rank of A equals order of highest non-zero minor. Minor means determinant of the square submatrix of the matrix. To understand this clearly, let's take any matrix n cross n. Let's name it A. Here the highest order is n, and det of matrix is not equal to 0. If det of matrix is not equal to 0, means it is non-zero minor. It is non-zero minor. So order of the highest non-zero minor, here n is the highest order and we get non-zero minor. So here rank of A is equal to n. Our next point is determinant of A n cross n equal to 0. Then rank of A n cross n is less than n. To understand this clearly, let's go by the definition. Here it is given there exists at least one non-zero minor of order R, but it is given that mod A equals to 0. Mod A means minor of order n is 0. Minor of order n is equal to 0 means rank will always be less than n when mod A means det of A is equal to 0. Next property is rank of identity matrix is equal to n. Yes, it will always be true. As we can see here, if we take 3 by 3 identity matrix, it is always in row echelon form, and the number of rows will give the rank of the matrix. Next is rank of A equals rank of A transpose. It is true as we can perform elementary operations on A and convert it into A transpose, and as we know that elementary operations does not alter the rank of the matrix. Same goes for here. A row of A into A transpose equals row of A transpose into A equals row of A. Next, row of diagonal matrix equals number of non-zero diagonal elements. Let's take a diagonal matrix. Let's say here it is 1, 2, 3. In diagonal matrix, only diagonal elements are 0 or non-zero. Every other element except diagonal is 0 in diagonal element matrix. In diagonal matrix. So here in this 3 by 3 matrix we can see non-zero diagonal elements are 3. So rank of matrix will be 3. Next is if A m cross n is not null matrix, then rank of A m cross n is less than or equal to minimum of m cross n. So if we take a rectangular matrix, let's say 1, 2, 3, 4, 5, 6, this is a 2 by 3 matrix. We know that rank of matrix is the order of the highest non-zero minor, and minor is only possible for subsquare matrix. So maximum possible square matrix here is 2 by 2. Maximum possible is 2 by 2. So rank will always be less than or equal to 2, means rank will always be less than or equal to minimum of m cross n. Minimum of m comma n. Row of AB is less than or equal to minimum of row A, row B. Next is row of A plus B is less than or equal to row of A plus row of B. Next is row of A minus B is greater than or equal to row of A minus row of B. These definitions are very important in the MCQ point of view. If row of A n cross n equals n, then row of adjoint A equals n. And if row of A n cross n is equal to n minus 1, then row of adjoint A is equal to 1. And if row of A n cross n is less than or equal to n minus 2, then row of adjoint of A equals to 0. It's better to remember this for MCQ exams. Thank you friends, thanks for watching. If you have any suggestions for next video or feedback for this video, please do comment. If you like this video, please do like, comment, share and subscribe. Thank you.